Welcome to EDU World Space.
In this problem, for the first part, we will be calculating the amount of power emitted by a person. Now for that, we need to consider the Stephen-Boltzmann law, which P equals A sigma T to the fourth power, which gives the power as a function of A, the area, sigma, the Stephen-Boltzmann constant, and the temperature. Now it's given that the area of a human is 1.4 meters squared, so we're going to go ahead and substitute that in. Stephen-Boltzmann constant in SI units is 5.67 into 10 to the negative 8, and the temperature of the surface of the skin is given as 306 Kelvin, and we're going to raise it to the fourth power. Now use a calculator to evaluate the expression. So the expression evaluates to 696 watts to three significant figures. And that's our answer to the first part. Now for the second part, we need to calculate the peak wavelength that the average person emits. For that, we will use the Levine displacement law, which gives lambda max as being equal to 0.0029 divided by the temperature of the emitting blackbody. So the temperature, as with the previous part, was given as 306 Kelvin. So we're going to go ahead and make that substitution. And now we're going to evaluate it using a calculator. And this evaluates to 9477 nanometers, which is about in the infrared range of the electromagnetic spectrum. Now for the next part, we need to determine the amount of energy absorbed by a person in a room that is at a temperature of 293 Kelvin. So we're going to go ahead and find out the power per unit area emitted by the surrounding. So power equals A sigma T to the fourth, dividing both sides by A results in sigma T to the fourth. Now the temperature of the average surrounding is given to be 293 Kelvin. So we're going to substitute the Stephen-Boltzmann constant and the temperature, 293 Kelvin, into the formula, and we're going to evaluate it with our calculator. And this comes out to be 418 watts per meter squared. Now it's given that the area of the human skin is 1.4 meters squared, so we can go ahead and make that substitution in our formula. So what we're left is 585 watts are being absorbed. And for our next part, to find the net power emitted, we need to subtract the power that is emitted, 696, from the power absorbed, which is 585. And subtracting these, results in 111 watts, which is our final answer for the last part.